Hey everyone, welcome back to our APIGURU channel. For those of you who are new here, I'm Damien Tone here. On this channel we share everything you need to know about APIs. Today we will explore the different API authentication schemes. Let's get started. Let's start by ensuring each one understands the difference between API authentication and authorization. API authentication verifies the identity of the user or software client making the request. In contrast, API authorization verifies that the authenticated user or software client has permission to access the requested resources. APIs typically include a mechanism to identify and authenticate software clients. Once authenticated, an API may additionally authorize the request to decide how it responds to it. Various schemes are commonly used, but each has limitations that could cause security problems if not implemented appropriately. Let me walk you through the different options. An API key is a static string value passed by software clients to your APIs with every request. API keys are widely used to identify software clients and are usually sent as query parameters or custom HTTP headers. However, when sent as query parameters, they are susceptible to being logged by intermediaries, increasing exposure risk. Additionally, API keys typically do not expire unless explicitly configured to do so and can easily be extracted from application code, making them vulnerable to exploitation. Let's move on with basic authentication. Basic authentication is a very simple authentication method. The software client sends an HTTP standard authorization header with each request that contains the word basic followed by a space and the base 64 encoded static username, password string, which is easily decoded. The decoded value of the example reveals the username admin and the password let me in. If the authorization header's value is compromised, an attacker could decode it and impersonate the associated identity. To mitigate this risk, basic authentication is typically used with HTTPS to provide confidentiality, and intermediary components or systems are usually configured not to log or capture the value of the authorization header. Let's move on with OAuth. OAuth is an open standard for access delegation that is widely used across the web. It allows users to grant software clients access to their information or resources without sharing their credentials. With OAuth, users can securely access their resources without revealing their usernames and passwords, ensuring their sensitive information remains protected. Client IDs and secrets serve as identifiers and authenticators for software clients. Access tokens permit access to specific resources for a set period. They can be revoked by the user who granted permission or the authorization server that issued them. Scopes can be used to define the level of access a token provides, limiting permissions to only what's necessary for the operation. Grant types cover the various scenarios OAuth supports for authentication, providing flexibility in different use cases. Lastly, TLS is required to protect tokens during transmission, ensuring all API traffic is encrypted for security. The OAuth 2.0 specification is a flexible authorization framework that describes several grants methods for a client application to acquire an access token, which represents a user's permission for the client to access the data, which can be used to authenticate a request to an API endpoint. This access token is also known as a bearer token. The different grant types should be used for different use cases. Let's break down each OAuth 2.0 grant type listed, explaining their usage, authentication requirements, and best practices. The client credentials grant type is typically used for server-to-server interactions without direct user involvement. It involves authenticating the client application itself rather than a specific user. The software client must authenticate using credentials, like client ID and secret, but no user authentication is involved because the application operates on its behalf. This grant type is recommended for scenarios where the application needs to access its resources or perform background tasks. The password grant type involves users providing their username and password directly to the client application. The client then exchanges these credentials for an access token. This method requires the client to authenticate itself and handle user credentials. While supported, it's not recommended for most cases due to security risks. Mainly because the client application has direct access to the user's password, it's typically only used for first-party applications, that is, apps developed by the same entity that owns the authentication system, where the risks can be better managed. The authorization code grant type is commonly used in user authentication scenarios through a client application. The process involves the user being redirected to an authorization server to log in, and then the authorization server redirects back to the client application with an authorization code. The client then exchanges this code for an access token. Both the software client and the user need to be authenticated. This grant type is recommended due to its security benefits. The implicit grant was previously recommended for native and browser-based applications whose client secrets cannot be revealed on the front end. For these scenarios, the implicit grant is a simplified authorization code flow that directly issues an access token without authenticating the client. In this flow, the access token is returned directly in the URL fragment after the user logs in. Since the client application does not authenticate itself and the token is exposed in the browser, this method is less secure and is generally not recommended. Instead, use the authorization code flow with PKCE for your native, mobile, and browser-based apps. For native and browser-based JavaScript apps, it is now widely considered the best practice to use the authorization code flow with the PKC extension instead of the implicit flow. This flow is like the regular authorization code flow, except PKCE replaces the client secret used in the standard authorization code flow with a one-time code challenge. This means the client app doesn't have to store a client secret. Let's move on with the access token used in all the flows. Opaque tokens are commonly used as access tokens in OAuth 2. The software client sends an HTTP standard authorization header with each request that contains the word bearer followed by a space and the token. The opaque token is a unique string representing the authentication and consent of all parties involved during the initial authorization process. This token is only meaningful to the authorization server that issued it. Typically, opaque tokens have a short lifespan ranging from 5 to 20 minutes. This limited validity helps reduce the risk of misuse if the token is exposed. Additionally, opaque tokens can be revoked before expiring, providing an extra layer of security. Opaque tokens should be stored securely and always be sent via TLS. Now let's speak about the JSON Web Tokens. JSON Web Tokens are also often used as access tokens in OAuth 2. They carry claims that the recipient can trust. The software client sends an HTTP standard authorization header with each request that contains the word bearer followed by a space and the token. The token creator uses encryption to create a signature. By decrypting the digital signature, the token recipient can verify that the token was signed by the authorization server and has not been modified since it was created. JSON Web Tokens can be verified without being sent to the authorization server. This is in contrast to an opaque token, which cannot be verified without sending it to the authorization server since there is no encoded value in the token itself. This makes the JSON Web Token very useful for microservices, where there might be several microservices for a single API call, and it would cause significant latency for each microservice to make a separate network call to verify the token. The flip side of this design is that JSON Web Tokens typically cannot be revoked. This is in contrast to an opaque token, which requires validation by an authorization server for each call and can be revoked before it expires. Therefore, the best practice is to keep the time to live for JSON Web Tokens short. JSON Web Tokens have three sections: header, payload, and signature. The first section is the header, a JSON structure with claims about the token. The head primarily specifies the algorithm used to generate the signature. In this case, the algorithm is HMAC SHA-256. The second section is the payload, which contains claims that convey information about the user and the permissions granted. The subclaim represents the user's unique identifier. It is used to identify the principal, user, or entity to whom the token was issued. The name claim provides the user's name or a human-readable representation of the user's identity. It helps identify the user more easily when interacting with the API. The IIT claim indicates the time the token was issued. It helps determine the token's age and can be used to implement token expiration and validity checks. The XP claim specifies when the token expires and when it should no longer be accepted. It ensures that the token is valid only for a certain period, enhancing security by limiting the duration of access. The scope claim is optional and can be used to limit access for a given token, granting permission only for necessary API operations. In this example, the token bearer would be authorized for the get photos operation. The ISS claim identifies the authorization server that issued the token. It helps to validate that the token came from a trusted source and can be used to verify its authenticity. Finally, the AUD claim specifies the token's intended recipient. This ensures that the token is used only by the intended API or resource server, preventing misuse by other parties. Let's move to the last section of the JSON Web Token. The last section is the signature. The signature guarantees the integrity of the token. The signature is created by signing the encoded header and payload with a secret key using the specified algorithm, for example, HMAC-SHA-256. The header shows HMAC-SHA-256 as the hashing function so that the signature will be a hash of the base 64 URL encoded header and payload separated by a dot. Note that this token is not encrypted. Like opaque Auth tokens, JSON Web tokens should be stored securely and always be sent via TLS. Let's compare the opaque and JSON Web token. JWTs are typically longer than opaque bearer tokens. This increased size is due to the inclusion of metadata and claims within the JWT, which adds additional data to the token compared to the compact opaque token, which only serves as an identifier. JWTs can be easily decoded to reveal their contents or payload as they are stored in a readable JSON format. However, this does not apply to JSON Web Encryption tokens, encrypted versions of JWTs designed to secure the payload from unauthorized access. Opaque tokens can be centrally revoked by updating or removing the tokens record in the token store, allowing for straightforward management of token validity. In contrast, the self-contained and stateless nature of JWTs makes revocation more challenging. Once issued, a JWT remains valid until it expires, and managing revocation typically requires additional mechanisms like blacklists. JWTs do not require a central storage database to persist in token information. JWTs are self-contained, meaning all necessary information is embedded within the token. In contrast, opaque tokens necessitate a centralized data store for tracking and validating token usage. The well-defined format of JWTs facilitates easier integration with various applications, platforms, and vendors. Their standardized structure makes them compatible across different systems and technologies, enhancing interoperability compared to the opaque tokens. JWTs utilize digital signatures to ensure the integrity of the header and payload claims. Any alteration of the token's content after issuance would invalidate the signature, thereby providing a mechanism to verify that the token has not been tampered with. Choosing between opaque tokens and JWTs often depends on the system's specific needs, including performance, scalability, and security considerations. Thanks for watching. If you enjoyed this video and want to see more, hit the subscribe button and turn on notifications so you don't miss any updates. Please give this video a thumbs up if you found it helpful and let me know what you think or if you have any questions in the comments. Look out for our next video in which we will share best practices for setting up an API security governance model that manages risk while enabling speed.